Hello everyone. In this video and several other following videos, I'm going to provide some lectures on digital controls. In this video, we're going to look at some basic terminologies and some components, and then we start the theory of basically discrete time, or you might call digital control systems. Okay, we start with Z transform and then the subsequent titles. Why do we need digital control? Now that we learned classic control, state space, a little bit about optimal control, adaptive control, nonlinear control, these are all done in continuous time, or you might call using analog signals, right? These are continuous control strategies. So why do we need to do digital? Because in today's industry, everything is digital. Your microcontroller, the computers, anything that you use, the PLCs that you use for controlling systems, they are digital by nature. So since these control algorithms are deployed to and are executed by computers and digital devices, so it's imperative, it's inevitable that you have to learn how to work with digital systems and to do some of these these control algorithms in the discrete space. So what is the workflow of a digital control system? Okay, what is the overall block diagram of it? This is what you can see. This is the input, this is the output, and this is the plant. Now, of course, here you have to add a bunch of more components to go from the input and output, which are typically analog, to inside the system where everything is digital. So you have to convert this analog signal here where everything is digital and then go back to analog again. Okay, so you need these components called A to D, analog to digital, and D to A, digital to analog converters. So digital control systems, they have more components, they are more expensive, but they come with a bunch of advantages. Okay, they are much more scalable. They can basically provide more accuracy and a lot of other advantages that we discuss when we talk about the controls later, but just wanted to tell you that. And typically the most expensive component is this A to D component. That is one of the most expensive components. So let's talk about that. And before I proceed any further, just wanted to tell you that the material in this video and probably in most of my upcoming videos are taken from this book, Discrete Time Control Systems by Ogata. I'm personally a big fan of the books by Ogata. His books are amazing, very well self-explanatory. They use MATLAB basically extensively, and you can easily learn from them. So I absolutely recommend this digital or discrete time control system by Ogata. Amazing book, just like his classic control book. So when the signal comes in, input output, one of the things is your output is going to be measured by a sensor, and the sensor or transducer, we're going to see about transducer, is going to convert it typically to a voltage, and there will be some inherent noise in this measurement process and quantization of the output signal. And so before you pass this noisy output to the system, which can easily throw off the system from its good performance, you have to typically apply a filter to the system, so you get a filtered version of Y where the high frequency noise components are reduced. So typically this is a low pass filter, or if it's a specific range of frequencies, it could be a notch filter or anything. But you send it in, so here you can generate the error signal E, and then here this E it could be analog, but now it has to be converted to digital signal. For that, we use this sampling and hold circuit and then A to D circuit, and everything here is synchronized by the clock of the system. And then once this digital signal is formed, so now it is going to be E of N times T instead of E of T, and it goes to a digital computer where your control algorithm resides. Okay, so here is your control algorithm in the discrete space. And then once that control signal U is created, which is like U of nt, now it's just a bunch of points. So now you have to convert it into a continuous signal. So first you use a D to A, we're going to talk about it. Then you use a hold circuit, and so now you're going to have some basically continuous signal which can be sent to the actuators. So actuators will apply their final control command, basically the whatever you want to call it, FT, whatever it is, to the system. Okay? And there might be some disturbance, of course, as well, which is going to directly affect the plant, or if you have a feed-forward controller, it can also affect that part as well. So the things that I want to talk about is this inner part, the digital control. This is what we're going to talk about. SH, sampling and hold, A to D, D to A, right? And the essence of the digital control in the digital computer. Here is another picture of that, where you can see some sample of the kind of signals that might exist in each part. So your command signal could be in general what an analog signal, and the output as well, okay, coming out of the plant. But look, as it goes into this digital portion, after S and H and A to D, now it is going to just be a bunch of zeros and ones, because that's the only thing this computer understands. Then this computer will generate, the control algorithm in this computer will generate some control signal. But again, this is a bunch of zeros and ones, but you cannot pass a bunch of zeros and ones to your actuators. So now you convert them into what with D to A, right? You convert them back into values that are not just zeros and ones. Maybe these are in the base of 10. Then you convert these discrete samples into a continuous signal, send them to the actuator. So actuator generates a continuous signal that can derive the output of the system. Okay, so let's look at the first part, which is converting an analog signal into a digital signal, which involves a sample and hold, or SNH, SH circuit, and analog to digital, or A to D circuit. What is the overall thing that they do? So first, you bring in an analog signal that has infinite resolution on the x-axis or vertical axis and the horizontal axis. So here, both of these axes, they have what? They have an infinite resolution. Means you can have any x value and any time value. In computer, that is not a possibility. You only have a limited resolution for either axis. The first thing you do, you use a sample and hold basically circuit, where let's say if it starts at this initial time point right here, then what it does, it holds the value of the signal at that level for so much of time, which is this. Then at the next time point, it reads the next value, so it comes, let's say, to here. Then it samples the signal again, so now it is here. So again, it keeps that value, hold it for so much time. Again, at next time, it goes and reads the signal, which is now here, and again, it keeps that, and it generates this. So now what you have is your vertical axis is quantized, basically. It's converted into a finite number of values, and now you don't have infinite number of values on the x-axis, right? So now you have a finite resolution on the x-axis, or in this case, the vertical axis here, but in the t-axis, still you can pick on any time that you want. So still your t is infinite. Now in computer, that's not a possibility. You can only have times at so many, let's say for instance, if it's what we call a periodic sampling, you can only have times at so much of a sampling time. So we can only have time at 0, t, let's say 2t, 3t, and so on, okay, where this t is called the sampling time. And now on this horizontal or the time axis, you also have what? Now you also have finite resolution on here as well. And now this is the part that we call sampling. So now your continuous time signal is converted to a discrete time signal. Yes. And now what? Now the next step is how many levels do you have here? You see here I have a value here, a value here, a value here, value, right? I have all these different values. And now how many of them can you keep? Can you keep all of them? Not necessarily, because in a computer you only have so many bits. So if you have n bits, in this case for this picture here on the right, let's say the computer you are using here only has 3 bits. If you have 3 bits, then you can only keep up to 2 to the 3, which is 8 levels. Okay? So here, if you count these levels on the right-hand side, you see there are 8 of them. So any number that you had out of the sampling stage now should be converted to the nearest value out of these 8 levels. So you have to do a rounding operation, right? For instance, if you look here, look, these two numbers are not the same, but now that we pick this as the highest level, then both of those that are closest to this highest level, now they have to be converted to the same number, you see? So here you had to increase this number a little bit, make it the same as the other one almost, or both of them the same as the highest level. So you see here, going from here to here, you have some round-off error or some quantization error. So the signal that you have here on the right side is clearly an approximation. It's never as accurate as the original signal, and it cannot be because you only have a finite resolution. So this is an approximation of this original one. Now this sampling operation and this quantization operation together, we call them A to D converter, and this initial part where you try to break this continuous curve into a bunch of what we call a stairway signal, right? Then we call it the sample and hold. Now, how do you physically do that? We're going to see something about the hold circuits and so on. My goal is not to go through all hardware details, but I want to give you an overall view of what is it that you are doing in a digital control system. So this sampling, the one that I showed you, is the sampling is done at basically regular intervals, which we call sampling time. So in general, it's like n times t, correct? So here you see your signal is x of t. In here, it's not really x of t anymore. In here is actually x of n times capital T. And here they are quantized to 8 levels. So this kind of sampling, which is the most common one, is called periodic sampling. But there are other ways too. One of them is called random sampling. So you're not going to basically pick these samples at specific time points. So the first one might be t, but the next one could be 1.5 t. The next one could be 3.2 t, and so on, which is not what the typical A to D does. And the other one is called multi-rate sampling. So you can have one circuit that samples it at rate T1. The other one can do it at sample rate T2 and T3 and so on. So you have several circuits, each one sampling at a different rate. Okay, then you might call it multi-rate sampling. So there are different ways to do sampling. Now, let me do a little bit theory here. If in general you use n bits to store the values and do the quantization, and the full scale range on the signal X, if we call it FSR, then the quantization level Q is given by that full scale range divided by 2 to the n, and the quantization error, which is the difference between the original continuous or analog signal and its discrete version y, which comes out of the quantizer, the difference between them can be only between 0 and q over 2. How come? Well, let me show you very fast. So let's say that we have what? We have a signal for which the full scale range, when we measure this signal, all possible range for this signal is anywhere between, let's say what? Let's say, for instance, 0 to, let's say 50. So the full scale range for this signal is from 0 to 50, or if you want the single number, it's 50, okay? So it goes from 0 to 50, or let's say 5 to 55, and the max minus min is 50. And so now, how many bits do we have to store these 50 values? Let's say we have what? Let's say we have, for instance, like 4 bits. So n equals 4. N equal 4 means the maximum number of levels you can have is 2 to the 4. Okay? Or 16 levels. What are they? Well, if you have 4 bits here, they can either be filled with a 0 and a 1. So the lowest level is all zeros, and the highest level is all ones. Right? So the lowest number is 0, the highest level is 15, so you have 16 levels. Okay, so now you have to break that 50 into 16 different levels. And again, let's say this corresponds to going from 0 to 50. So you set your lowest level 0 corresponding to the lowest level, and then you break down this 50 to 16 levels. So you calculate this Q. In this case, it's going to be 50 divided by 16. How much is it? It is 3.125. Okay? Yeah? So that is the Q level. So now what? Now if you have any number that is 0 to this number, so any number between 0 to 3.125 should be assigned to 0. Let's say any number between 3.125 to 2 times that, which is like 6.25, that should be stored to, let's say, this level, for instance. Any number between, let's say, 6.25 and 3 times that, which is 9.375, correct? That should be like 6.25, and so on and so forth, right? So all the way you come to some number here to 50, and that number should be 46.875. Let's say that number corresponds to 46.875. Or if you start on the right hand side, then you can say the first one is 3.125, so this last one corresponds to 50. You see, so now this continuous range of 0 to 50 is only broken into 16 different numbers. You have to use one of these 16 different numbers and show that continuous signal between 0 to 50 now only at these 16 different levels. So this distance between each level and the next is exactly this Q that you have at full scale range divided by what? 2 to the n. Now how much is error? Well, your actual signal when you go from this level to the next, right, in this continuous manner. Okay, so let me clean this up. So here you have 2 levels, this level and this level, and your actual signal is somewhere here. Okay, and your quantized level is either this one or this one. Okay, so your y of t is either this or that, and your x of t is somewhere in between. So this difference here could be basically at max Q over 2. Because what? Because if it passes this midpoint, it is going to go to this. If it's below the midpoint, it is going to go to this. If it passes above the midpoint, it can go to that. Okay, so if it's in this region, it is going to be rounded to the upper level. If it is in the bottom region, it is going to be rounded to the bottom level. So you really can only have at maximum Q over 2 error. Okay, that is the level of error that you can get. And of course, the bigger the n, the smaller the q, the smaller the level of quantization error. But of course, you can only have so many bits in a computer. One other mathematical thing that I want to explain is if q is significantly small, then the distribution of this quantization error would be kind of something like a random noise. Okay? So if you plot this E of t, it is not going to be a perfect Gaussian distribution or uniform. It's mostly kind of like a random noise. And by the way, here is another good picture that shows you the original continuous signal x versus the quantized signal y, which is a stairway or staircase signal. And this is y as a function of x and the rounding operation. Now, if we want to find the variance on this quantization error, that's not easy because we need to know what kind of distribution. If we assume this distribution is uniform so it can be anywhere between negative Q2 to Q2, it's a uniform distribution, which is a common thing for a white noise, basically, then you can say that the variance of this error is going to be 1 over Q, integral from negative Q to Q over 2 to positive Q over 2 of sigma squared dA, and it is going to be Q to the 3 over 12. Just a little bit of statistics on this error, just wanted to tell you. Now, let's look at some other components that you need when you go from an analog signal to a digital one. So the first thing you do when you have a physical analog signal, you have to measure it, you have to sense it, and that is done by a sensor, or in general, you might call it a transducer. What is transducer? Transducer is a device that converts one type of physical quantity to another, and most of the time the output of a transducer is a voltage. So this could be, for instance, temperature, or pressure, or whatever it is, velocity, acceleration, anything, and this is a voltage most of the times, because voltage is the easiest thing to handle in electrical components and digital computers. Sometimes we need to use an amplifier to amplify this voltage because the output voltage of a transducer is typically not big enough to pass through filter and lots of other sample hold and A to D converter and so on. Okay, so for instance, a change of maybe 100 degrees Fahrenheit can only create a range of maybe, I don't know, so many millivolts or something, which is really gonna easily be mixed with the noise, okay, that is coming through the measurement process, right? Because this conversion of signal to voltage also involves some noise. And if this output is not really amplified enough, then passing it to low-pass filter might not be a good idea, because you might just remove all of the original signal. So most of the time you need to combine it with an amplifier to amplify this, get rid of the noise, as we said. One of the things is in a analog to digital conversion is what we call a multiplexer, or in MATLAB you see it as called MUX. What is it? I'll tell you, and then sample and hold and A to D converter, which we kind of see. So let's explain them a little bit more. So what is a multiplexer or a MUX? MUX is a multiple switch device. which allows for time sharing when you have several channels and you want to convert all of these analog signals into their digital signal, right? Before you send them to the SH and A to D, if you have several signals coming from different transducers, you can do time sharing and send them one at a time to the SH and A to D devices. Why can you do that? Because these times that you need to sample them here, these are typically very short times, these T's. Okay, and in between these, you see that you are not doing anything. Your sampling device is only switched on at those stems at those specific times, and then it turns off. So all of these gaps here are when your sampler device could be basically on idle. Can I pass in between all these gaps another signal to be sampled? Yes. That is the idea of time sharing. So you use this multiple switch device, and each time you're going to only turn one of them on and the rest of them are off, or one of them closed, the rest of them open. So the signals are sent one at a time to the sampler and be used so your system can act faster. So this device is called a multiplexer, and typically the order using which these switches are made open and close is determined by a component called a sequencer. So we can either start with the first one, go all the way to last, or we might use a specific, maybe first one, fourth one, eighth one, then second one, fifth one, and so on and so forth. And most of the time the number of channels is a power of 2, but and you might not need to use all of them. So if you have 8 channels, do I need to have 8 signals? No, maybe I only have 2 signals. Okay, but still I can do time sharing and accelerate the performance of the system. And as I said in MATLAB, I'm going to show you is this block here called MUX, which you can combine. You see here I combine a sine signal and a cosine signal and make this composite signal, right? And let me show you that right now, actually. Since I made this small demo for you, let me show you. So here I have a sine wave and I have a cosine wave. All I did by adding a phase shift of pi over 2. And I combine them into this one composite signal, which I can show on this single scope. You see here, that's my sine in red, cosine in blue, and this is a composite signal. Or I can later break this composite signal into the initial constituent signals, right, the forming signals, separate them, sine and cosine, and send them separately to a scope with 2 ports, or you can send them to individual if you want. If you don't like this, you can basically send one here and one here, right? And then you can call this sine scope, and you can call this what? Cosine scope. Okay, so you can now individually do anything you want to them, including monitoring them. Yeah. So this one that breaks down the composite signal into the components, the elements of it, is called demux or demultiplexer. And here I just showed you the mux, but the mux is kind of similar structure. Okay, you probably, if you use MATLAB and Simulink, you definitely know about mux and demux. So let's go back. Now we said that one of the components we have is this basically sample and hold, right? S and H, which converts this signal into this staircase or stairway signal. How does it do it? Let's take a look. One common way for a S&H circuit is a couple of op amps or operational amplifiers, a capacitor, and then a basically clock or a device that sends the command for the switch to be turned on and off. The input to it is analog, the output to it is still analog. Don't think that it is digital. Look here. This is still analog. You have the signal for any time point. And here too, it's just the vertical axis is now at specific levels instead of infinite resolution. So both of them are still analog. Here is analog, here is analog, here it goes to digital. So we are talking about this portion now. So how does it do it? You have a couple of op amps. The first one is the buffer for the input. The second one is the buffer for the output. The voltage, which is stored across this capacitor, is exactly the one that is gonna match the input voltage or input signal that is coming from the transducer. And this capacitor is a high quality capacitor that has very small leakage, and by leakage means a drop in the voltage. Okay, so it can retain the amplitude of the signal. So how does it work? First, you close the circuit. So now the capacitor circuit is closed. The voltage across the capacitor is trying to match the input voltage. So from initial condition, it starts going up like this until you order the opening of the circuit. But since when you order it, it's not that command is not going to be executed immediately, and there is a little bit lag time known as what we call the aperture time, then the voltage of the capacitor goes up a little bit further, so it goes up to here. Now the circuit opens up, and ideally you expect this level of voltage to go like that and stay at the constant level, but there is always a little bit leakage, so the voltage starts to drop a little bit. This is where the capacitor tries to hold the voltage at the same level. It cannot. So if it's a good capacitor, the slope of this drop is small, and this is how it is going to behave. So when you look at the output of the SNH circuit, it's not going to be straight like this, perfect, and it is, as you can see, it is basically coming from here, go up, then drops a little bit, then go up, and then drops a little bit like that. Okay, so you have two modes: a tracking mode where the circuit is closed, your voltage across capacitor matches the input, and then a little bit lag, and then the hold mode where the capacitor tries to keep the voltage. It has a little bit leakage, so it drops a little bit, and this is the operation of this SNH circuit. And the opening and the closing of the switch is done through your sampler command. Okay, so it depends on when you want this circuit to be opened and when you want it to be closed. So this typically is controlled through some pulses, right? When it's above some level, it is going to close. When it's below some level, it is going to open, and so on and so forth. Okay, so this is the SNH circuit, and as I said, then we have the A to D converter where it takes this analog signal, and then it only captures the value of it at specific time points, and of course then it converts it to so many levels. This can be done all in software. For this you don't necessarily need the hardware, but if you want, you can also do some portion of it, specifically this level. If you want, you can do it in hardware, but mostly, as I said, this A to D can be done, a huge portion of it, in software. So now on the other hand, when you have this digital signal, and now this digital signal is going to be sent to the controller makes a decision based on this digital signal, which is typically your error signal, and generates the output signal, which the output signal is also digital. Now you cannot pass that digital signal to your actuator, so now you have to convert this digital signal back into what? Back into analog, and that's where you need the D2A, or digital to analog converter. And that conversion in general has some process like this. So you get the digital control signal from the controller, you register it. If there are several signals coming from the controller, before sending them to the individual actuators, you need to break them down into the individual elements. So you might need a demultiplexer. Then you need to do D2A converter, and then you need a hold circuit, which is the main part, which converts all of those individual signals into basically something like that. So there are different mechanisms for D to A converter. Let's talk about that. Here we just look at one of the mechanisms. There is the ladder mechanism as well. Here we look at the circuit that is called weighted resistor circuit. But as I said, there are other methods as well. And then we're going to look at the hold system too, and mathematically describe it a little bit, because the hold is similar to this hold that we had earlier, right? Basically this here. So let's talk about this D to A conversion. So here, this reference value, when it comes in, it's a binary, it's a digital, or it's a binary basically value. For instance, let's say if it has 4 bits, this value, the value for the signal B is something like B0, B1, B2, and B3. And then each one of these bits is responsible for what? For closing or opening one of these switches. Okay? So depending on which one of these bits is 1, that switch can close, or if it's 0, that switch is going to open. And based on that, you are going to have what? You are going to have the total output voltage to be equal to the ratio between R0 and R, and this total summation of all of these bits times what we reference. And also you see that the values of these resistors are also in a binary fashion. So it's 1R, 2R, 4, and 8, which corresponds to basically these denominators here. Okay, so the circuit will convert here, this one, a 4-bit binary number into basically an appropriate value that can now be held to generate the analog signal, right? So right now, basically, you can say this portion is converting a binary number into something that is decimal number. And now that that decimal is generated, I'm going to use a hold circuit to keep that level of decimal constant between one sample time and what? The next sample time. So I can get an analog signal, something like that. Okay? Now, there are different ways to hold the value of a voltage over a sample time, and one of them, which is the most common one, is called zero order hold, and there is another one called first order hold, there is second order hold, and so on. So here I just want to show you zero and first order hold. In zero order hold, what you can see is wherever I start, I'm going to keep that level fixed for that entire time period between one sample time to the next, and then I'm gonna again keep the next level constant, the next level constant, and next level constant. So you see a bunch of stairs or step functions. Now for the first order hold, it's a little bit more interesting. Take a look how it does it. Let me zoom in a little bit if I can, so I can show you what it does. Now when I start here, okay, I don't know my next value, okay? You're just reading the values one at a time. So I don't know my next values here. So initially, for the first period, I just go increase it with some slope like that. Now, when the next value comes in and it's registered and converted to decimals using A to D, now I know what? Now I know it's this number. So now for the next period between t and 2t, I try to say, hey, hopefully the slope that was between 0 and t, which is this slope, hopefully that slope stays the same for what? For going from t to 2t. So I assume that the slope is going to stay constant. So when you want to go from t to 2t, use the slope from the first part. By using these two previous data points, the current one and the previous one, you go by this line. You see this line is the continuing of this line. Then when the third sample comes in, it's not coming here, it actually comes there. And so now you calculate the slope, you say, well, seems like the slope is updated to this guy now. So now when I want to go for the value at 3t, between 2t to 3t, I assume the slope should what? Should stay the same as this new one. So now I'm going to go with this. And so I end up here, but guess what? When the number comes in, you see the number was there. So now you have to, again, adjust the slope and say, well, seems like this is the new slope. So let's keep it. And so you go with this and you have somewhat some offsets. But if you look at these offsets, which I can show you by these shaded areas, the shaded areas here are the areas of error, the areas that the approximation is not what the same as, of course, the actual signal, the deviations. So these are these shaded regions here, right? If you look at their size and their shape, you see they are not as bad as the zero order hold. Okay, so now for zero order hold, these are the regions of deviation, and you see they are quite a bit bigger. So overall, keeping a higher order for hold makes the approximation better, but at some expense. What is the expense? The expense is you have to calculate the slope each time. So you need to do some mathematical operation as well. Or if it's a second order hold, you have to calculate now the parabola and try to keep the same curvature and initial slope and everything of the parabola. Okay? Here, you don't need to do any calculation. Whatever comes at time 0, you keep it the same until t. Whatever comes at t, you keep it all the way to 2t, and so on. So this is simpler to implement. This needs more computation, but this is a little bit more accurate. And you have those things in MATLAB as well. So for the last part, I want to just briefly show you my second demo here. This is a sine wave, and I don't want you to make a mistake here. The sine wave is not a continuous. This is not an analog signal. This is still a digital signal. Why? Because it resides in my computer. It cannot be analog. But here, so how does it look like? It looks like this. If you really want to see it, you can create a scope and then do a stem plot, and the actual shape of that signal is what I'm about to show you. This is the shape of that signal, really. So when you see that beautiful sine in MATLAB, it doesn't really mean it's a sine, it's a continuous sine. It's just a bunch of numbers that MATLAB connects together for you with some small lines. And the smaller the sample time, the worse the shape of it is going to be. The bigger the sample time. The smaller the sample time is, it is going to be smoother and nicer. Okay, so that's the. It's not really as I said, it's not really an analog signal. But if you apply a zero order hold on it, this guy, or apply a first order hold on it, I want you to compare the original signal versus zero order hold and first order hold. And zero order hold, if you double click on it, it only has a sample time. First order hold, if you click on it, it has some initial input, output. For output algorithm, it has a slow method which avoids overshoot, and it has a fast method which minimizes the error. And by default, the first order hold does not accept this kind of signal, which is called continuous input. Again, when it says continuous, in terms of MATLAB, it's continuous, not in terms of real world. So if you want to connect this kind of signal to it, you have to activate this option. If you don't, it's not going to accept it. And let me show you the difference between the sine versus zero order and first order hold. So here the green is the sine wave and the blue is the zero order hold. Let me zoom into one area so you can see it better. There we go. Look. Seems like I made a mistake. Let's bring it back. There we go. So as you can see, for zero order hold, you have a bunch of these stairs. It keeps them the same between one sample and the next. And remember, the sample time varied was 0.1. So of course, this is the output of zero order hold. Now for first order hold, you see it connects them by a line. And since the sample time of it is not big, actually the first order hold does a relatively good job of mimicking the actual signal, except for a little bit kind of delay, phase delay. And that is because it doesn't have any information to update the slope until the next time point comes in, and then starts updating the slope. The last thing I want to tell you is about the effect of quantization levels. Remember that if you have n bits, q is the total range divided by 2 to the n. So here I brought in this quantizer block, and let's here say that I only have 8 bits to store the whole range for a sine wave. That the whole range for a sine wave goes from -1 to 1, so it's just 2. And if I have 8 bits, then the quantization level q is going to be 2 divided by 2 to the 8, which is about 0.0078. And if I do that and apply that quantization level to the sine, let's see what kind of shape we are going to get. And here is the result of that. So you see, if my computer only had 8 bits, then the blue is what you can see out of the sine wave. But right now, look, my sine wave is much better than that. So it means that my quantization level is smaller. That means the number of bits that I'm using to store these values in MATLAB is quite a bit larger than 8 bits. And you can clearly see the effect of that and the quantization error. So I'm going to upload this for you, although that's very basic thing. I just wanted to tell you about doing a stem plot, about zero order hold, first order hold, the quantizer blot, mux, and the mux, which many of them you know, but this might be good for your basic learning. So this is the basic of digital control. In future videos, I'm going to get into theory of that along with MATLAB examples. Probably the next one you're going to see from me is the Z transform. Thank you so much for your attention. I will see you in the next video.